My name is Sydney, and I will be talking about generating probabilistic safety guarantees for neural network controllers. Neural networks are able to represent complex functions and therefore are able to represent complex control policies in high-dimensional settings such as self-driving cars or autonomous aircraft. But before we put a neural network behind the wheel of a car or in the cockpit of a plane, we want to ensure that they'll operate safely. However, due to their complex nature, it can be difficult to predict what a neural network will do across all possible scenarios. For this reason, the use of neural networks in these types of applications has been limited up to this point. In this work, I'll use aircraft collision avoidance as a motivating example. An airborne collision avoidance system called ACAS-X, which became an international standard for manned aircraft a couple of years ago, represents the collision avoidance policies as large numeric lookup tables. And while this approach works really well, the lookup table takes up storage capacity on the order of gigabytes, which can exceed the storage capacity of some small aircraft and therefore limits the use of this method on these vehicles. For this reason, recent work has approximated the table as a neural network, and not only does the neural network perform as well as the table in simulation, it requires significantly less storage capacity, representing over a 1,000 times decrease in storage requirements. However, simulations are not enough to guarantee that the neural network will perform safely in all possible scenarios, and again, its behavior can be difficult to predict. Thus, if we want to see the significant benefits of neural networks in safety-critical applications such as this one, we need to develop techniques to verify their performance, which is the primary motivation behind this work. My method for verifying the safety of neural networks is motivated by techniques in MDP model checking. MDPs encode sequential decision-making problems. We can use dynamic programming to solve for the optimal value function and use that to define a policy that maps from states to actions. We will assume in this case that we are already given this policy in the form of a neural network that we would like to verify. In MDP model checking, we are trying to determine the probability of satisfying some linear temporal logic formula from any state in our state space, given that we follow policy pi. So for example, in the aircraft collision avoidance problem, we're interested in whether or not the policy will result in a near mid-air collision, or an NMAC. This translates to the LTL formula eventually NMAC, meaning do we eventually end up in an NMAC state? And it turns out that for any LTL formula, this problem can be converted to a reachability problem. In this case, doing so is pretty simple. We're just interested in the probability of reaching any state in the NMAC region. So to summarize, our goal is to find the probability of reaching an NMAC state for any state in the state space, given that we follow our neural network policy pi. We'll call this probability PR superscript pi of s. For states in the NMAC region, this probability is simply 1. For states not in the NMAC region, this probability can be calculated using the recursive formula shown here. This formula actually looks a lot like the Bellman equation that we use to solve for the value function of an MDP. And in fact, solving for these probabilities is equivalent to solving for the value function of an MDP with a specific reward function. And so what this means is that we can use traditional dynamic programming methods, such as value iteration, to find these probabilities. So now we have a way to find the probability of collision from any state in the state space. And this is great. So why don't we just do this for neural networks? Well, here's an example of a 2D slice of the collision avoidance policy, where the colors represent the action at that particular point in the state space. So for example, clear of conflict, do not climb, etc. However, even just in this 2D slice of the state space, we have an infinite number of states to evaluate, and therefore we cannot possibly calculate this probability at every single state. So our solution is to divide the state space into a finite number of cells, and instead evaluate the probability at each cell. To do this, we need to modify our model checking formulation to work with cells rather than states. Previously, we had a policy pi that maps from a particular state in the state space to a specific action in the action space. Now, we will instead define a policy called pi tilde, which maps from cells in the space of possible cells to subsets of the action space, since multiple actions may occur within a cell. We also need to then update our recursive formula to work with cells. We are now determining the probability using our over-approximated policy, pi tilde, and because this policy maps to subsets of actions rather than a single action, we need to introduce a maximization that assumes that we take the worst case action in that subset. So in order to summarize, we basically have two steps. The first step is to obtain an over-approximated policy, pi tilde, and then the second step is to use that over-approximated policy to perform model checking, and that is what will give us our over-approximated probability of collision. I will first talk about how to obtain the over-approximated policy. Again, we want to map cells in the space of possible cells to subsets of the action space. To discuss how to do this, let's look at this example cell. This cell looks like it evaluates entirely to the green action, or climb at 1500 feet per minute. However, this plot was generated by evaluating a finite number of points, so there's no guarantee that if we zoom in on this region and evaluate more of these points, we won't find some other action, such as clear of conflict. So then how are we going to be able to determine the action subset for a cell without evaluating an infinite number of points? Well, it turns out that a lot of the recently developed neural network verification tools can do exactly this. I will not get into the nitty-gritty of how these tools work, but for our purposes, we can think of them as taking a region, such as this one, and outputting a guarantee of all actions that are possible at some point in that region. So for example, this region would output climb at 1500 feet per minute for every single point in that region. For this region, it would output clear of conflict and climb at 1500 feet per minute. And in general, our neural verification tool takes in a cell, C, and it will output the action subset that we were looking for. So what makes this policy an over-approximated policy is the fact that we are mapping to action subsets rather than to single actions. Thus, we have this maximization in our recursive formula, assuming that we take the worst case action possible at some point in the cell from any point in the cell. Therefore, any cell with more than one possible action will contribute to over-approximation error. For example, the cell on the left maps to only one possible advisory. So the maximization in the recursive formula essentially disappears, and there's no over-approximation error in this cell, in contrast to the cell on the right, which maps to multiple possible advisories. So with this in mind, when we split our input space into cells, we want to do so in such a way that minimizes the volume of the input space covered by cells that have multiple possible advisories in order to minimize our over-approximation error. To accomplish this, we came up with an adaptive verification strategy. We start by running a cell through the verification tool in order to obtain the action subset. Next, if the action subset contains more than one action, we simply split the cell. And we continue to do this until all cells are either below a minimum cell size or contain only one action. So I'll illustrate this method on a 2D slice of the state space shown here. The plot on the left shows the policy, and the plot on the right shows the number of actions in each cell. Blue cells have one possible action, red cells have two, and yellow cells have three or more. Thus, to have a small amount of over-approximation error, we would hope that by the time we're finished, the plot on the right will have a lot more blue in it. So we start with a single cell encompassing the entire input space. There are 4 actions possible, so we split the cell. All of the resulting cells still have multiple actions possible, so we split each cell again. Now we are making some progress, and we have some blue cells that we don't need to split anymore, but we'll continue to split the others until they reach a minimum cell size. As we make splits, the cells start to zero in on the decision boundaries of the network, and they result in a policy with a small amount of over-approximation error. Our plot is covered by a lot of blue. We also developed a slightly faster splitting strategy that takes advantage of network evaluations at the corner points of each cell, and we showed that both strategies are significantly faster than a uniform splitting strategy, in which all of the cells are just the minimum cell size used in the adaptive verification. Before I show the results of model checking after we obtain this over-approximated policy, I want to describe the dynamic model that we use in this work. So the state contains the relative altitude between the ownship and intruder aircraft, the vertical rate of each aircraft, and the time to loss of horizontal separation, which we call tau. So when tau is near 0, we want the aircraft to have a high vertical separation in order to avoid a collision, because this is the point in which they've lost all of their horizontal separation. In order to provide probabilistic guarantees, we need to specify a stochastic dynamics model. We do this by just assuming a distribution over the acceleration of the ownship given a particular collision avoidance advisory. We also need to modify the transition model to work with cells rather than states. I'll illustrate this with a simple example. Let this be our current cell and possible next cells, and say the action is clear of conflict. With 0.34 probability, the acceleration is 0, and I end up in the shaded region shown here. This region overlaps with multiple next cells, so in order to preserve the over-approximation in our probability estimate, I assign all of the probability to the cell with the highest estimated probability of collision. So for example, maybe it's the center cell here. And then I can repeat this for the other accelerations as well, again assigning all of the probability to the cell that contains the worst case next state. So then we can perform model checking using this model, and this is the result that we get. The plot on the left shows the discretization of the space, and the plot on the right shows the probabilities. The vertical axis is the relative altitude between the two aircraft, and the horizontal axis is the time to loss of horizontal separation. If we assume that aircraft encounters are initialized with 40 seconds to loss of horizontal separation, we can use the estimates at tau equals 40 to determine the probability of collision. So therefore, we want the probability to be low on the right end of the plot. Therefore, what this plot tells us is that the probability of collision is less than or equal to 1, which is not a very meaningful estimate. Thus, in order to produce a more meaningful estimate, we need to further reduce over-approximation error. We already reduced policy over-approximation error using our adaptive verification method, but the second source of error is the worst-case transition error, in which we assume that every point in the cell transitions to the worst-case next state for any point in the cell, which I showed on the previous slide. In order to reduce this type of over-approximation error, we do so during the solving process by borrowing ideas from state abstraction. If the range of collision probabilities in the region of next cells exceeds some threshold, then we split the current cell. So when the threshold is set to 1, we do not make any splits because that's the maximum possible range for probabilities, so we'll never exceed this threshold. However, as we begin to decrease this threshold, we begin to split the cells in safety-critical regions of the state space, as you can see by the dense band that's forming in the center of the state space. And the over-approximation error starts to decrease. Eventually, the over-approximation error decreases to the point where we are able to produce a reasonable over-approximation of the collision probability, with a maximum probability around 0.03 at tau equals 40. And even finer resolutions will produce an even tighter estimate. To wrap up, we've outlined a method to generate probabilistic safety guarantees on a neural network controller. We developed an adaptive verification method to obtain a neural network policy, an over-approximated neural network policy, and showed how we can use online splitting heuristics to reduce over-approximation error during the solving process in order to produce meaningful estimates. Overall, this represents a step towards the ability to verify the safety of neural network controllers so that safety-critical applications may experience their benefits.